My name is Sam. The very first thing I want to say is a quick shout out to the person who's led this project from start to finish. It's been a monumental effort. So it's Sophie Johnson sitting at the back who has been leading this, as well as doing loads of other stuff for her PhD. Really, most of the credit here should go to her. That's the very first. There's more acknowledgements at the end. What I've given it away. If I was to ask you what the single greatest figure ever published in a scientific paper was, what would come to mind? For me, it's this one. This is from Howard Eichenbaum in 1999, and it's trying to get this idea that mammals that we all use our spatial memory system to learn about abstract non-spatial concepts and reason about them to solve complicated and difficult problems, abstract problems. So to give you a bit of an indication of what I mean by this, I've got a couple of examples. I'm only going to focus on one of them. In this study, published in 2016, the authors trained participants to learn a bunch of different birds that they made up. These birds were characterized by differences in their neck length and their leg length. And because those two features, neck length and leg length, varied independently of each other, you could conceive of these birds, these artificial stimuli, as kind of existing in this two-dimensional, stretchy bird space, okay? And the authors found patterns of activity in the human spatial memory system that indicated that participants were using their spatial memory systems in order to recognize those bird stimuli and reason about them. Now, the problem with studies like this, I think, and that hasn't been addressed until now, is that these tasks kind of implicitly guide participants into thinking about these stimuli in a spatial-like way. So, for instance, they often ask relational questions between the stimuli. Which stimuli is better than this one? Or, kind of in this particular task, participants were actually, they could manipulate the leg length of the birds and the neck length of the birds independently. So they could actively walk through the space, the bird space, and that's how they detected these patterns in the spatial memory system. So it's not yet clear if you have a task that actually doesn't have any hint of any spatial relationships, whether the spatial memory system kind of is involved. Now, it turns out that you can get artificial neural networks to learn these kinds of concepts. And indeed, the transformer architecture has been implicated as a model that, with some kind of changes, can learn spatial-like relationships. This is a study from Power et al. 2022. And what they did was they trained very, very simple one-layer neural networks, so one-layer transformers that kind of to learn modular addition operations over integers. And they found various things, but one of the key things is that you get some kind of spatial-like organization in the neural network. It learns spatial-like representations of its inputs. So here, this is a network trained on the integers mod 8, and you'll see a representation of 0 down here, 1, 2, 3, 4 is there, 5. So you see this four-fold rotational symmetry in the representations that this neural network is learning. So that's all good. But one thing that is surprising about these networks when they learn these particular tasks is they actually start generalizing what they've learned long after the point that they've completely memorized their training set. Okay, so here is a curve showing the network's performance on a set of directly trained, supervised modular division operations. This is in this case, and generalization actually happens long after that. So it's not quite known whether humans exhibit that same kind of it's called the Grokking effect, like delay between generalization and memorization. So these were our research questions. Do humans learn kind of these, can they generalize abstract conceptual relationships learned from these small algorithmic data sets like modular addition? Do they show that very long, prolonged period of kind of delay between memorization and generalization? And do they use their spatial memory systems in order to solve these kinds of tasks when the task doesn't directly imply any kind of relationships between the task stimuli or kind of any hint of spatial information, that spatial information is relevant to the task. So this was how we trained what we got participants to do over many, many weeks on people's phones. They performed this kind of little game, you can think of it as. It was basically modular addition. So it was modular addition mod 6. And each integer in our task was associated with this very, very abstract kind of squiggle. We call them sparks. So each of these was associated with an integer value between 0 and 5. And we got participants to perform an addition operation over these stimuli by showing 2 of those stimuli in a sequence, followed by this little squiggle thing here, which kind of indicates like an addition plus sort of operator. And then participants had to use trial and error to kind of, they had as many attempts as they needed to get the right answer. So we could track learning on a set of supervised questions over this 5x5 addition grid. Now, we also had a couple where we also had quite a few unsupervised questions, and we carved those up into different types. So there's an easy type and a hard type of unsupervised problem in this. The easy type is where you can kind of use some sort of heuristic in order to solve get the answer. So for instance, if you imagine 4 plus 1 is actually unsupervised, but 1 plus 4 is supervised. So, and because addition is commutative, you can very easily kind of figure out that what the answer is to that. We call those commutable unsupervised. They're pretty easy. The hardest ones, the ones that we really cared about in this study, were these non-commutative unsupervised questions, like 3 plus 3, okay? There's no other way to get that other than to just learn the structure of the task. 2 plus 1, 1 plus 2. So those are the things that we looked at. Okay, I'm short of time, so I'm going to speed through the results. Do humans show this grokking phenomenon? Yes and no, maybe is the answer. So these are their supervised performance on the supervised performance on for all participants. Each participant is an individual line, and they learn at a particular rate with a particular onset. They learn anything with 0 plus very quickly as well. And they learn anything, those unsupervised commutable pairs, they learn those pretty quickly as well. What we did was we looked to test the grokking hypothesis. We looked at memorization points. So basically when supervised performance was about 99% accuracy. And we compared that to the learning onset of these unsupervised non-commutative pairs. So is there this long delay between when they start generalizing and when they finished learning? Okay, and there isn't. There's evidence. We found evidence that they start generalizing well before the supervised offsets. Do we see the spatial memory system in this? The answer is yes. So we basically scanned people as they did the task. We recorded pattern representations for each of these stimuli, and I'm going to cut a long story short here, but in the anterior hippocampus, you do find patterns of activity that are indicative of these stimuli. They show this modular distance between all of these stimuli only if you have performed the task very well. So when participants actually learnt to generalize, we found patterns of activity that indicated that they had learned the modular distances in their spatial memory system. That's actually in 2 regions, the entorhinal cortex and the anterior hippocampus. So I will end now. I'm sorry, I know I'm over time. Thank you to, I've mentioned Sophie already, Ivor Simpson, whose initial kind of discussions on this project kind of cottoned me onto some of these ideas. Kate Howland, who I've been working on related projects with this. Chris Bird, Claire Lancaster, Jane Oathill, and Jenny Rusters, who are long-standing collaborators. Thank you all for listening, and download the pre-reg. You can also have a look at our GitHub repos on this project as well. Thanks very much.
Okay, thanks, Sam. And I'm sure we'd have all liked to have heard more detail about the project. I think we've got time for like 1 question. So anyone got a question over there? You want to go, Ivor? Or you can shout.
just about the imaging results at the end, how you were trying to how that shows that it's map-like.
Well, so what we did was we recorded patterns of activity for each of those image stimuli, correlated those patterns of activity with each other to find, and then looked for this very characteristic pattern similarity effect. So basically, was the zero image, very, very similar to the one image? You would expect that because if you go to this kind of circular structure applied by this modular addition kind of structure, 0 should be very, very similar to 1. It should be kind of similar to 2, yeah? And it should be very dissimilar from 3, okay? So we looked for this very characteristic pattern similarity effect between the stimuli. And you do, as I say, you do find it in the anterior hippocampus bilaterally and anterior entorhinal cortex bilaterally, which is predicted by those theories, but only when people have really learnt the structure and can generalize them. Yeah.
Okay, thank you. Thanks, Sam, again.